Hello, everyone, and welcome to our presentation. We are the Mosquito Spray Wind Tunnel team, and the team members in this team include Jerem Anderson, Colin Dincher, Brandon Perkins, and Benjamin Shriver. And our advisor for this project is Dr. Meredith Metzger. So to start, we would like to give you a brief introduction of our project. So the government organization which we have been working with during this project is the Salt Lake City Mosquito Abatement District, which is a district responsible for controlling the population of mosquitoes in Salt Lake City, Utah. So this district has asked us to design and fabricate a mosquito spray wind tunnel in order to allow their technicians to perform pesticide testing on mosquitoes in a controlled environment. The reason they want to perform these tests is because the better they understand or know the effectiveness of the pesticides they're using on the mosquitoes, the better they're able to control the population of mosquitoes in Salt Lake City. Now, Colin will talk about the specifications of the project.
So when we were designing our solution to this project, we had a couple objectives in mind. We wanted it to be repeatable, which is measured by air flow rate and pesticide coverage. On the air flow rate, we were given a goal of 3 to 10 miles an hour because a typical pesticide is applied in that range. And our wind tunnel that we'll talk more about in the future here, it achieves a goal of 4 to 16 miles an hour. And that can be dropped down to even lower speeds if we added another filter. For the pesticide coverage, we did some testing and found that we have 100% coverage over the 6-inch cross section of our tunnel for the mosquito cage. It is accessible. Due to our design, we can insert the mosquito cages very quickly in under 10 seconds, and that also makes it pretty easy to disassemble and clean. It is inexpensive. We came in under budget, and we're feeling pretty happy about that. Because of how accessible the mosquito cage is, it's also very cleanable. As I mentioned, things can be taken apart very quickly, and that means that it can be cleaned in under 5 minutes. It's also portable. The largest dimension is 5 feet, which gives our volume of 5 cubic feet, and it fits in a passenger car, as well as safe. Safe is one of the objectives that we were conscious of, to make sure that as we're operating the wind tunnel, no pesticide is leaking out. And as a result, we have weather stripping on all of the gaps in our assembly to make sure that there are 0 gaps and everything is airtight when in operation. Now, Jerem will talk a little bit more in depth about the design solution.
Hey guys, we gave this design solution a lot of thought. We wanted it to be able to disassemble very easily, so we tried to innovate ways to be able to disassemble it quickly, but be able to have it airtight as well. Brandon, you can point to the steel frame. It's the main support of this whole thing. Each of the components attached to it, basically. On the top of the frame sits the T, the 6-inch T. It has an inlet for the fan, so we can adjust the airflow. And on the top is the place that pipe sticking out is where the hose, the air hose, and the wires for the Arduino, which control the airbrush nozzle is. If you look at the bottom picture, that is the airbrush nozzle. It's an off-the-shelf unit, Badger model, usually for art and whatnot. It's connected to an air hose, like I said, and it's got a servo actuation, so we can be able to time the amount of pesticide. You can point to the Arduino. It's the red box on the frame there. It's got buttons to control the amount of time that the pesticide is dispersed, and it will be able to, I guess, give the right dosage with the other calculations that we've given them. One of the more important things on this is the mosquito latch area, the mosquito cage latch. So if you open that, you can get the mosquito cage in and out very quickly and easily, and close it up. It's weather stripped, so it's airtight for the most part. The hinges were printed, and all the clear PVC tube right in the middle, which you see, you can look inside and see the mosquitoes flying around in the cage down below, and you can see the airbrush servo actuate when you push the button to ensure that it sprays. At the bottom of the frame, there's the outlet filter on the elbow there. It's is able to filter out most of the pesticide droplets and very fine particles as well. So we're not polluting or getting the lab full of pesticide or anything like that. It's replaceable, and you could also stack more filters on if you want a slower speed or anything like that to achieve a 1 or 2 mile per hour range if you'd like. Going on from that, there's an important part which Colin wants to explain about the analysis.
Yeah, so the analysis, we did an FEA analysis on the T, because the T is what helps mount this bracket here is what helps mount the T to our steel frame, and it is holding a lot of the weight of our project. And because it is printed in ABS, we were a little bit concerned about the strength of it, because 3D printed ABS, we weren't sure if it had the same strength properties as injection molded ABS or something similar. So we did an FEA analysis on it, and we ended up finding that we had a factor of safety of 32. As a group, that made us very confident that it was going to support the weight of our tunnel, and we didn't have anything to worry about with that. In terms of meeting our metric of repeatable with 100% coverage, we wanted to do a study on the jet width as a function of distance from the nozzle. So figure 5 here shows distance away from the nozzle, and then the y-axis is how far the jet has spread in that time frame. So at 2 feet from the nozzle, we can see that the spread is well beyond double of the width of the cross section, which means that we'll have dense uniform coverage. Next, we'll kind of talk about the testing results. Brandon will take us away with that.
Yeah, so moving on to testing and results, our first main concern when starting this project last semester was making sure that we could get droplets in the size range SlickMad specified. So they specified they wanted droplets between 15 and 19 microns. To figure that out, we needed to test our airbrush nozzle at different pressures. Initially, we thought that we wouldn't be able to get droplets that small. So we began testing at higher pressures, like 40, 45 PSI, stuff like that. And we found we actually had the opposite problem. All the droplets were too small. So we continuously kept testing and bumping down the pressure as we went. And we found that at or below 20 PSI, we reached that 15 to 19 micron range. So you can see here from our testing at 20 PSI, is sort of the threshold. We got an average droplet size of 15.76 microns. So that confirmed that we could get in that range that SlickMad wanted. So with that in mind, we tested and figured out the volumetric flow rate through the nozzle at 10 and 15 psi. So and with different needle positions of 1.5 and 2 turns out. These needle positions are what adjust the nozzle to determine how open or closed it is. So we figured this out so that when SlickMad does their testing, they can determine how long they need to spray pesticide through the nozzle to get a certain amount of pesticide for the test. So say at 10 psi they get 0.6 microliters per second. Well, depending on how much pesticide they want to use, they use the Arduino controller to determine how much time that nozzle will spray to get the specific amount of pesticide they want. Next, we tested, we did UV dye testing. This was to validate our calculation right here about the jet width and to make sure that we had uniform coverage and we didn't have any sort of gaps, and made sure that we got the entire width diameter of the mosquito cage. So we did this by laying a paper towel on our mosquito cage across the entire cross section of that cage. So you can see right here, this is 6 inches in diameter. So we laid that on, and then we filled up our nozzle with UV dye and sprayed onto it. So you can see here we got complete coverage. There's no gaps, and it goes all the way to the very edge of the mosquito cage. Next, we'll move on to the velocity profile with Ben.
Okay, the last test that we performed was the velocity profile test. So the reason that we performed this test was because SlickMath specified that the air velocity before the mosquito cage needed to fall within the range of 3 to 10 miles per hour. So using a pedostatic tube, we measured the air velocity while moving along a fixed axis in 1-inch increments. Yeah. And in the figure to the right, figure 8, you can see the measurements that we took during this test. So one line represents one orientation when we took measurements, and another line represents another orientation we took measurements. So the first orientation was when the pedostatic tube was perpendicular to the adjustable speed fan, and then the second orientation was when the pedostatic tube was parallel to the adjustable speed fan. So after collecting this data, we took the average and found that the average airspeed with a low fan setting is 4.53 miles per hour with a 10.6% variation across the pipe. So from our data, we can conclude that we did meet that requirement of an air velocity. So now Brandon will show you a video on how to operate the mosquito spray wind tunnel.
Yeah, so earlier on, a couple weeks ago, like I was saying before the presentation, we actually were able to work on the project, different components of the project on our own, taking them home and stuff like that after the pandemic hit, carefully working on whatever we could. Eventually, we all met up at SlickMad to deliver the final project and set it all up and show them how it works. So this video will kind of show how it works, how it's set up, and all the different components. So we begin with inserting the mosquito cage. It's that simple. That goes to our metric of accessible, so the mosquito cage can be inserted quickly and easily in under 10 seconds. Next, we'll move on to the actually operating the device. So you can see here, you just pull this out and then inject the pesticide that you want to do into the reservoir, and then just pop that back in like that. Then you turn on the fan setting to whatever you want. You can see it's an adjustable fan, so you have many different options. That's why it's between 4 and 16 miles per hour with the adjustable fan setting. Then you turn on the battery and then adjust the Arduino timer to whatever that is. So it's in increments of 100 milliseconds, and that's how long it will spray. You can see right here how long it will spray the pesticide into the tunnel. And you can see the compressor hooked up right there. Next, this is just showing how it works, that we can actually spray. We 3D printed a little stopper right here to make sure none of the pesticide gets out and that they're able to hold a good amount of pesticide within the chamber. And here's the servo actuator that will press the button for however long we specify using the Arduino controller. Next, this is just taking the mosquito cage out. Just undo the toggle clamp and pull it on out. Very simple. We didn't test with pesticide this time. It was just oil at that point. For changing the actual pipe to clean it, you just pull up on that pipe that Jerem just pulled up on, and then you undo this toggle latch and then the bottom toggle latch. And we 3D printed a little handle here, so it's very easy to just pull right out, like so. And then you end up just pulling this off, and then you can clean the entire thing really easily where it matters. Next, we'll show just putting it back together. Just pop that right back in, and then pop this back in. and close it up with the toggle latches again. Quick, easy, completely sealed, no issues. And you can see right here the mounts that we had. That's what we did the FE analysis on. And we had a lot of 3D printed parts. You can see all the latches, the handle, the mounts, the finger guard, the pretty much anything that's colored. And that's us delivering it, being safe as much as we can. And that is everything. Any questions?